Questions about anything? Last time or anything? I thought it'd be a good idea to say a few more words about the business about the square root of 2 exists. I might have convinced you what the square root of 2 is when I was messing around with rational numbers whose square is less than 2. And we kind of invented, Dedekind invented Dedekind cuts to think about that. And it was the inspiration for trying to figure out the least upper bound property. So, but it's hard to convince people that, there's a problem with figuring out the square root of 2 exists. We want to know the square root of 2 exists from the axioms and the first principles of analysis. And so it's the axioms that we've been studying, the order properties, and now the new least upper bound property. That's a new thing. And that's what we're using to deduce this fact. So let me pull up, something I frequently do is when I go back to my office, I look carefully at the notes, and if I've made any slip-ups, I fix them. So if you ever think, ooh, that doesn't seem right, you might go look in the notes that I post afterwards and see that I fixed it. So let's see, last time, the idea about showing the square root of exists is we take that thing that was a Dedekind cut, and instead of taking the rational numbers, we take all the S positive real numbers whose square is less than 2. And Dedekind sort of thought, okay, I'll invent cuts and make those be rational numbers and define the square root of 2 to be that. And then he demonstrated that it works. And he also demonstrated the least upper bound property is a fact about that when you use that definition of real numbers. Anyway, now we're going to see that we can demonstrate that the number we get this way actually does have the property that its square is 2. So we take that set of numbers whose square is less than 2, and we're expecting the square root of 2 to be its least upper bound. That's the plan. And so we know the trichotomy property of real numbers is that, so the R is the supremum of that set. Either R squared is equal to, or less than 2, or greater than 2. Those are the only possibilities. And we're going to see that we can deduce contradictions if R squared is less than 2 or greater than 2. And last time I handled the case R squared less than 2. So the idea was if R squared was less than 2, then maybe I could squeak it up a little bit and keep it less than 2. And that's, of course, that's your gut feeling, and your gut feeling is right. So if R squared happened to be less than 2, then I would look at R plus 1 over n, something really small, and square that, and hope that I could make that also less than 2. Okay, so there's the picture. There's R squared on the number line, and I want to squeeze R plus 1 over n squared in between there. And that's going to violate something. I'll explain what it violates in a second. Well, I played around with it last time and realized that, yeah, that's not hard to do. If I choose 1 over n small enough, then I see an inequality I need to make it happen. And the inequality is that n needs to be greater than a certain thing. Those are positive numbers, by the way. And we know that the Archimedean property allows us to find such an n. Okay? So I can cook up an R plus 1 over n whose square is less than 2. Okay, now here's what I didn't say enough about last time. So we have R plus 1 over n squared is less than 2. that means that r plus 1 over n is in S. Since its square is less than 2, it's in the set capital S. Well, guess what? That means that the r is not an upper bound for S, because r is less than that. So that's what I didn't say last time, and that's what I added to my notes. And so that contradiction means it can't be the case that r squared is less than 2. Okay, and now I'm going to start today's subject. Any questions about that before I... Oh, well, let's see. The least upper bound of that set would be 0, because it's that blue line that goes from 0 to the square root of 2. So we don't care about the least upper bound. Yeah, that's the easy side. The interesting side is the square root of 2 side. And that's where you squeeze down and get the soup. The soup is all the upper... You have all the upper bounds. The soup is the least upper bound. So we squeeze that right down till it hits the square root of 2. And of course, we have to show that that really does happen. Okay, so before I move on to today's subject, which is more of Cantor's big ideas, I'm going to do the case. I'm proving that the square root of 2 exists. So remember, S is equal to the numbers in positive real numbers such that S squared is less than 2, and R is the soup of S, and we're expecting that to be the number we want. That's going to be the square root of 2, which means that R squared is equal to S. So R squared greater than S, R squared greater than 2, less than 2. That's what I did last time. Done. Last time. You get a contradiction. Now let's the case R squared bigger than 2. We're going to get a contradiction here too, but it's going to be kind of a different contradiction. So I was going to skip it and let you read it in the book, but I think it's worth talking about, so make it easier for you to read it in the book. So instead of looking at R plus, so let's see, my number line picture now is, here's 2, R squared is bigger now. And my idea is to try to cook up something that's stuck in here that's a little bit less than R. So that's going to be an R, instead of plus 1 over n, it's going to be R minus 1 over n squared. I want to stick it in there. And then that's going to, if I can find such a thing, it's going to be give me a contradiction. Okay, and let me explain how I'm going to do it. So let's think about R minus 1 over n squared. That's R squared minus 2R times 1 over n plus 1 over n squared. Well, this time the plus 1 over n squared just makes that bigger. So that's less than, this thing is positive. So this thing is strictly less than R squared minus 2 over R times 1 over n. And I want that, let's see, what do I want? R squared minus this. I want that to be something less, and I want to stick it right between 2 and R squared. So how do I would get that. I want this to be less than the distance there. And that distance is R squared minus 2. Okay, I'm at the purple R squared. I'm going to squeeze over a little bit, and I want it to be less than that total distance that I move to the left. Okay, well that's very easy to arrange. So you see, aha, I need, let's see, I need 2r times 1 over n to be less than r squared minus 2, which means I need 1 over n. By the way, these things are positive. R squared minus 2 is positive, 2r is positive, so I should mention that that's positive. Remember, one of the corollaries of the Archimedean property is you can get, you can make n as big as you want, or you can make 1 over n as small as you want. They're very related, and I demonstrated that last time. But so let's see what I need n bigger than, invert this and get 2r over r squared minus 2. And once again, I can do that by the Archimedean property. And so now think about what I've got. Let's see. So I'm thinking now. R squared. Oh. Okay. Here's the thing that's, if I locked you in a room and said, don't come out until you can show me this is true, you'd have to think about this step. If S is in S, then S squared is less than 2. That's the definition of the S. And now we have this other thing that's less than r minus 1 over n squared. And you stare at that for a second. And the thing that's making you, maybe it feels weird, is that there's a 2 in there. And you don't want to take the square root of 2, but you don't know the square root of 2 exists. But so here's the breakthrough. When I have s squared is less than r minus 1 over n squared. And so that one of the corollaries from the axioms is that when those are positive numbers, so that it's important to remark positive squares of something positive. When you're talking about squares of something positive, that can only happen if the numbers are also less than each other. And this is the breakthrough moment. Remember, r is the least upper bound. But I just showed you, give me any s and s, then s has to be less than r minus 1 over n. And so here's the big what. R minus 1 over n is an upper bound. And you think about that for a second. That can't be because r is the least upper bound. So that's less than r. And r is the least upper bound. So it's pretty, I don't know, it's a whole page of kind of hard work and careful thinking. I guess that's what math is like, but it's worth thinking about and understanding. Because you really have to understand what the meaning of the words and the definitions at a very precise level. It's the least upper bound. So that's where the contradiction comes in. And that means it can't be that r squared is bigger than 2. The last case then is that r squared must be equal to 2. Yeah. That's the trichotomy. And that's the end of the demonstration. Questions about that?
There is a step within the like if we prove 2r plus 1 over n is less than r squared minus 2.
What?
If we go there are some steps. Yeah, some steps where we prove n is greater than.
That's the n. We need to choose an n that's bigger than that. And then I have the r minus 1 over n squared that's stuck in that interval right where I want it. Right, so I should have said, okay, I can find such an n. I pick an n that's bigger than that. And that my Archimedean property means there exists such an n. And that's what I needed. Okay, I guess I said that without writing it down. Other question back there?
Can you scroll a little bit more? Maybe put the sign on equality. So r squared minus 2r 1 over n plus 1 over n squared. Wouldn't that be greater than r squared minus 2r times 1 over n?
Oh, that's what I want, isn't it? R,
And then you want to be under r squared, right?
r squared plus, oh, it's greater than. What? Am I messing this up? Right. Duh. It's greater, r minus 1 is greater than. R squared minus this is greater than that. Oh yeah, so this is even greater than that. I think that fixes it. Okay, sorry about that. It was right in my notes. Okay, well, I'm going to say we now know that the square of 2 exists. And of course, there's nothing special about 2. We know that the square root of any positive real number exists. Of course, I'm not going to do it again, but a fact, square roots of positive reals make sense. For square root of s for positive s. Exists too. So we're done with that. And now I want to move on to the next little topic, which is a really fun one. It's Cantor. Cantor had 2 proofs that the real numbers are uncountable. And the first one, I think, is the easy one. The second one is the one I showed you before. But the first one he did was based on a very elementary fact. Well, it wasn't elementary at the time because they were trying to figure out the foundations of analysis. And so people like Weierstrass, Dedekind, and that whole crowd were inventing this stuff so they could understand these ideas. And some of those ideas weren't quite 100% vernacular at the time. So Cantor used a fact about nested closed intervals. They have to be closed for this to work. I'll call this the nested closed intervals theorem. I think the book calls it a property. Okay, so a closed interval, I'll call it I sub n, is going to be a sub n, comma b sub n. And of course, that's equal to the set of x such that an is less than or equal to x is less than or equal to bn. That's a closed interval because the endpoints are in there. The open interval would have round brackets on the ends. Okay, so the nested closed interval theorem is that I've got a bunch of intervals, I1 containing I2, containing I3, etc., ... And when you think about what that means we've got a big interval, A1, A2, A1, B1. And then we have another one that's contained in that. So that would be an A2. Here's a picture of that. A2, B2. And then an A3. I could have this next one contained in it if the B3 was the same as the B2. So they'd both be the same. That would be okay. And similar, I could have some A's be the same. So I could have this A4 be the same as this A4, B4. They could share that same point, et cetera, et cetera. And so I have an A5, and you can feel it. The theorem is there's going to be something in the intersection. Okay, et cetera. So I should say ... I can't fit any dots in there. ... The theorem is the intersection is not empty. Intersection of the INs as n goes from 1 to infinity is not the empty set. So there exists a thing in there. There exists an R in that intersection, meaning that there's an R that's in all of them. There is an R such that R is in each IN for all n. Okay, that's the theorem. And since I'm dying to talk about what Cantor did with this theorem, I'm going to defer the demonstration of this until next time. Right now I'll sketch it. You can believe it. So here's a sketch of the proof, summary of the proof basically. And after I told you this sketch, you could figure it out yourself. Let's see. So the B's are shrinking down and the A's are sneaking up. So what would be if you think about the intersection, the soup, every A is bounded by every B. So all those A's are less than B1, for example. So they're bounded from above. So the soup of the A's is going to be less than or equal to R, is going to be less than or equal to the inf of the B's. The B's are shrinking downwards. So I'm going to have to show that that soup is less than or equal to that inf. And if R is between there, then it's in all the ANs. That's not hard to show. It's just you have to use the words and believe it. Okay, so then I'll do the proof next time. It's not hard. In fact, I could make it an exercise now that I told you what it's all about. But here's what Cantor did with that. So the fact is, Cantor knew this. He might not have been able to prove it. It was people like Weierstrass and Dedekind who were working on proofs at that time, but I would say he believed this. Let's assume it for now. And so here's Cantor's first proof that the real numbers are uncountable. Okay, let's suppose, so of course we're going to do it by contradiction. Suppose R is countable. R is clearly infinite because it contains the natural numbers. So let's suppose R is countable. So remember what countable means. It means either finite or it's infinite, but it can be put into one correspondence with the natural numbers. It's infinite because, for example, the natural numbers are in there. So countable in this case means that it can be put into one, so it's not finite. So countable means there exists a phi from n into r that's one-to-one and onto. That's what countable means in this context. If it was finite, it just means you could count it. That's why I just say that it's infinite. Okay. Well, describe how we're going to do this. First, I'll draw a picture. Let's let xn be equal to the phi of n. All right. We'll start with an x1. Okay, and it's like Cantor's diagonal argument. I'm going to take an interval, B1, doesn't contain x1. Okay, that's step one. That's going to be my I1. So that's the picture. X1's any old thing. I just pick any old interval that doesn't contain x1. Now x2 could be someplace. I'll draw a picture where x2 might be. X2 might be over here. Well, then I could leave this interval to be the same, because x2 isn't in that either. But if x2 is in here, I pick an interval that doesn't contain x2 that's a subinterval of the previous one. So this would be an A2, B2, maybe, etc. And very quickly, it gets really hard to draw the picture. Okay, so I'll say step one. That's going to give me nested intervals. Step one. An interval that doesn't contain x1. So x1 is in R. Pick any old interval, a closed interval, it has to be closed. A1, B1, such that x1 is not in A1, B1, like in the picture. Okay, step 2. Is we pick an interval A2 B2 contained in A1 B1 such that X2 not A1 B1. What am I trying to say? I mean, sorry, it's not in the second one. Okay, interesting. I mean, if A2 is outside of that interval, then here's a remark. You can always do that, and it's even easier if X2 is not even in there. If X2 is outside the first interval, if it's outside A1, B1, then you can take the second interval to be the same as the first interval. I2 to be the same I1. So this one is I1, this one's I2, etc. Okay, and of course I can keep doing this. Do I need to say one more? I think, etc. Step 3, I cook up A3, B3 contained in the previous one such that X3 is not in A3, B3. This way I get a telescoping, I like telescoping better than nested, but I get a nested sequence of intervals. So the aha moment is the nested closed interval theorem gives us an R that's in the intersection. And that means R is in every one of those intervals. R would be in each one. This is a diagonal argument. Let's see, so could it be X3? No, because X3 is in I3. So this means R is unequal to Xn because Xn is in In, R isn't. So R does not get hit by the phi. Not get hit by the phi map. That means phi is not onto. And so the one-to-one onto correspondence just can't be done. So it's fiendishly clever, that diagonal argument. And it comes up lots of places. Questions about that? Since I kind of want to have some fun today and slow down and think about some stuff, diagonal argument was in the air, and people realize how sneaky and useful it is. So you probably heard this story someplace before. Remember Cantor's theorem? The power set of S is strictly bigger, a bigger infinity. So what does it mean? Cantor's theorem was there's no map from S onto the power set. That's what I showed. And that means that that's a strictly bigger than a bigger infinity, a bigger cardinality. That's the set of all subsets. Okay, so it's a bigger infinity. And of course I can take the power set of the thing. So so the words here, P sub the power set is a bigger infinity. The word that got used has a bigger cardinality, is a bigger infinity than S. And of course, the power set of the power set, think about that, the set of all sets of subsets of S is even bigger. And you can keep doing that. Okay, so dot, 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 there's no biggest infinity. Okay, and Cantor did it in such a way that everybody believed it, you know. You can do this thing, and it's true, and you believe it. But then Russell started messing around with sort of philosophical questions about, you know, we're talking about humongously big sets. How big of a set can you talk about and still be speaking truth? So famous Russell's paradox. Has everybody seen Russell's paradox? New? They probably didn't want to scare you. It's horrifying. Russell's paradox. Let's let S equal the set of all sets. That's a really big set. The set of all sets. What don't I call that? I'm going to call that U for universe. Let U be the set of all sets. Let S equal the sets, the A in U, such that A is not in itself. That set is not in itself. Is that what I want to say? It's not a subset of itself, sorry. Not a subset of itself. Then you ask yourself, where is S? Is S a subset of itself or not a subset of itself? And both cases don't make sense. Is S in S? Is that what I'm trying to, who knows Russell's paradox? Am I saying it right? I thought it, yeah, okay. Is S in itself or is it not in itself? It's either in itself or it's not in itself. So so if S is a subset of S, you get a, think about what the contradiction would be. Either S is a subset of itself or it isn't. Okay, if it's a subset of itself, it's not in itself, because S is the set that aren't subsets of itself. Yeah.
Search for the paradox. It's as A is not.
What?
It should be
It's not subset, it's in, okay. I don't know what happened to me just now. A is not in itself. Okay, thanks for doing that for me. Okay, if S is in itself, then it doesn't satisfy that property there, so it's not in that set. So it, okay, or S. Okay, if S is in itself, it violates the A. I mean, think of A equals S and stick it in there, and you see that, oops, it doesn't satisfy that thing. Which means that it's in that set. What? If S is in itself, oh, then it's not in S. Because it doesn't, that's the case. If it's in itself, then it doesn't satisfy that. So, and that's a contradiction. This is a tongue twister when you think about it. And if S is not in itself, then it satisfies that condition, and so it has to be in itself. So S is in S. Contradiction. So either way, I get a contradiction. And so suddenly the floor fell out of all of math because it said, oh my God, set theory is inconsistent. Okay. And so there are the piano postulates about integers. Later on, there were the Zermelo-Fraenkel axioms of set theory. So the horror is set theory seems to be inconsistent. And the fact is that set is just too big. But this is very related to Cantor's breakthrough of a diagonal argument. That theory might be inconsistent. And so mathematicians got in a panic to figure out how to fix this. There's Zermelo-Fraenkel Frankel axioms of set theory. And so the whole industry was built up studying how to fix this thing. You can't let sets get so big that you can talk about the set of all sets. Question?
I think that a little earlier, it was a small typo, but either like S is not an S or S like it should be released in. Like that's just it.
Thank you. Yeah, that's what I was thinking, but I didn't write it. So now people have calmed down since then and realized, okay, we just have to be careful about how big we let our sets get. Taking the integers and the power set and the power set and the power set doesn't get to the things that are big enough to make this problematic. And so the things we study in math, like the real numbers and the complex numbers, don't get big enough that you have to worry about this. But you're definitely not allowed to talk about the set of all sets in math, because you get laughed out of the room. So you have to be careful about how big you think you're talking about your sets. Sets that might not exist because they're just too big. But in studying this problem, there was a whole bunch of other very subtle questions that came up. There's something that's very related to this called the axiom of choice, which leads to similar paradoxes. And so the big questions of math are, is set theory consistent? Can I deduce a contradiction from the axioms? And what do I have to do to avoid that? And even the question is number theory, the basic facts about notches on a stick. And coming up with an axiomatic description of number theory, which is called first order logic, the big question is that consistent? And how would you prove that it's consistent? And that's what Gödel was thinking about. And he had two famous theorems. One was that you can always come up with undecidable things that are not provable. They're true but not provable from the axioms. Then you can add them as an axiom and still have a consistent theory. The second incompleteness theorem was you can't prove that number theory is consistent inside number theory. You have to go outside number theory and create bigger things, bigger structures to prove that. Anyway, I thought it'd be fun to blow your mind for the last 10 minutes, but don't let this scare you away from doing math. We can do math without worrying about this too much. I never worry about it. Question?
Yeah, so this paradox is obviously built on sets like A that are not in A.
Yeah.
Could you explain that a little further? I'm having trouble understanding.
Let's see, what's a set that's in itself?
Or a set that like isn't in itself.
That should be on the tip of my tongue. We were looking at the Wikipedia page. What's the standard set that's in itself? A set of natural numbers, a subset of the natural numbers. I'll bring this up next time. My logic teacher always compared this Russell's paradox to the barber shaves everybody who does not shave themselves, who shaves the barber. It's a very similar thing. It's sort of the Cantor's diagonal trick. I'll come here next time with a set that's not in it, that's in itself.